So we continue with the next speaker, who is Stefano Curtarolo. He is the Edmund Pratt Junior School Distinguished Professor of Mechanical Engineering and Material Science, Professor of the Department of Mechanical Engineering and Material Science at Duke University, Director of the Center of Autonomous Materials Design, Professor of Department of Electrical Computer Engineering, Professor on the Department of Physics, Faculty Network Member of the Energy Initiative. So is this all? And actually, I added one line. He's the initiator and director of the A-Flow Consortium. Stefano, we are very happy that you are here and actually telling us about from data to knowledge. Please.
Thank you for the introduction. Can you hear me?
Yes, very good.
Okay, let me share the screen. Okay, so thank you very much for the introduction way too many things. So my name is Stefano Curtarolo and I work at Duke University, and I've been around the big data for more than 20 years. And lately we have been trying to understand science and phenomena from data, not only generating data, I understand what we can extract, right? Understanding what we believe is science, right? So I want to thank my sponsor. My sponsor is Office of Naval Research, the Army, and the National Science Foundation, the FAIR-DI infrastructures, which we collaborated through Matthias. And that's it pretty much, right? So today we're going to talk about the disorder ceramics, which is what we have been studying the last few years, and how data can teach us something. All right, so we started these things around 6-7 years ago, our interest in ceramics. Okay, so why ceramics? Well, first of all, why disorder? It's actually quite obvious, because we want more functionalities, we want to add species, we want to have more complicated materials, and then what happens that when you add more species to your system, the system suddenly becomes like a miracle, becomes a disorder, and you cannot control the disorder anymore. So the idea is if you cannot control something, just embrace disorder and see if we can get something out of disorder, right? So you can see what we can do with particular disorder in ceramics in this review that we published a couple of years ago, right? And also to help Elon Musk that wants to go to Mars and the land and without an impact. Okay, so where is disorder, right? This is an example of disorder. This is a simple phase diagrams, copper nickel, right? So you see that you have, if you increase the temperature, you have an area in the center where there is a high macroscopic entropy and low microstructure entropy. This is the area of what is called solid solution, because both copper and nickel are FCC, so everything becomes a solid solution and substitution alloy. If you decrease the temperature, you see that you have this line. This line is called miscibility gap, and under this line you have what is called a low microscopic entropy. Okay, because think about if copper were black and nickel were white, then you would have some sort of phase separation, which can be bimodal or can be spinodal, depending which part of the phase diagrams you are. And then you have a low microscopic entropy, because copper likes copper, nickel likes nickel, but at the same time you have this kind of spaghetti organization, which is some sort of microstructure, which actually gives you high macroscopic entropy. And if you look at the articles of ZQ Liu, he calls this mentropy, macroscopic entropy, mentropy, right? So you can, and you have a lot of properties, right, of this microstructures, like hardness, like ductility, etc., etc. And all these things has been known for a while, but we want to understand when these things appear. So the idea of understanding order disorder is to figure out a quick way to get these miscibility gaps. And we can use big data with that. First of all, when does it happen as a function of number of species? How many species you need to add before you find this disorder? And this actually was one of the first applications for us of big data, right? This became what we call the N+1 theorem, which is based on the delta convex solve, right? So let's do a Gedanken experiment, right? How they would call in Germany, right? So we will take all the possible elements A and B. There are 100 A, 99B, right? So you pretty much have 5,000 phase diagrams, right? So we have been accumulating data in the repository since 2003. Okay, so we have roughly 20 years of data, actually probably even more, right? Since 2000 when I was doing my PhD, right? And then actually you created these constructions, which are convex sols, and then you find the minimum formation entropy. So this is the Gibbs free energy at 0 temperature. Okay, so the red ones are VASPA calculation, quantum calculation, and you get this envelope. By the way, all this data is available online with our you can download with our REST API or through Nomad, etc., etc. So everything is accessible if people wants to do their own statistics. Okay, so you do this 5,000 convex sols, and you do an average of them, and you get an expectation of enthalpy for 2 species. Okay, which is this point, average this point, etc., right? So this is just a number. Okay, you do also for ternaries. Ternaries is more complicated because you have 100, 99, 98, so you have many more. So you pretty much you have 30,000. We want to do also for quaternaries and for pentanaries. So the problem gets bigger and bigger, but the idea is exactly the same. This is an example of a 3-dimensional convex sol, and everything can be done online. You can explore, click the buttons, and then check the formation enthalpies and properties and the entries, etc., etc. Okay, so this is really visually an example of visualization. Anyway, you do this for a ternary, right? And remember that you have a number, and you do all the averages. But be careful, because here there is kind of a trick, because look at point inside. This point inside needs to be better than all the other points, but also better than the decomposition of the 3 binaries, right? So A, B, B, C, C, A. So how better is this point with respect to the binaries is as good as the decomposition of the other 3 binaries, and that's what is going to be called the delta convex sol, and I will show you next slides. Anyway, you get these numbers, okay, and you understand where I go. You see that going from binaries to ternaries, you have a gain because you are keep digging this convex sol. Then therefore you're going to have a gain to go from n to n plus 1, and you do not know when you have a threshold, and this is what we need to discover. Okay, this is an example of what I meant before, right? This is a 3-dimensional phase diagrams, right? So this is exactly the rotating movie that but sliced. And if you want at this point, you want to understand how good is this point with respect to disorder, you need to see what is the decomposition with respect to the n minus 1 sub decompositions. Okay, so a ternary compound is as good as its 3 2 decompositions. Okay, the 2 decomposition, which are 3, generates an hyperspace, right? Sorry, an hyperplane, 1, 2, and 3. It's like, right, you have three lines. So on 3 lines, you get a plane, and the distance from this plane is exactly the gain that a real ternary compound has. Okay, and you can do this all with just analysis of the data. That's actually very simple. This was the enabler to understand when disorder takes over, because remember that if the 3 binaries are ordered, then this ternary needs to be better in disorder than the 3 binaries order, right? Okay, so this is what we call delta convex sol, and this is a very short paper. It's like 1 page, so you can read in less than 10 minutes. And practically, when you have this delta H, is the recursive expansion of the convex sol. All the sum of this delta H gives you the convex sol, but only the last piece gives you the order-disorder transitions, all in this very short article. Okay, so now let's get this delta, right? This is the delta, the gain of increasing number of species as a function of the number of species, right? This, this is decreasing, of course, because it gets harder and harder to dig in the phase diagrams. But at the same time, the more species you add, okay, and the more you generate disorder, because in the brown one, this brown is the ideal entropy x log x, which in this case is going to be log of the species, where everything is disorder. Okay, you see that there is a threshold. Here, this the second one, if there is one sublattice that remains order, or two sublattices that remain order, or three, etc., etc. But from these pictures, which is just an estimation at room temperature, you understand that already that there are three areas of interest with respect to the number of species. If you have a few species, let's say less than 4, everything is determined by the enthalpy. So you just minimize the enthalpy on your phase diagrams, and that's what we have been doing for the last 30 years with genetic algorithms, with cluster expansions. We always like to minimize the enthalpy to find the most stable configuration, and it works beautifully. So for minimum number of species, you just minimize enthalpy. For a higher number of species, let's say beyond the 5 and 6, these are completely entropy stabilized system. You don't care anymore about enthalpy. You care only about entropy, but the problem then becomes finding entropy, which is highly untrivial, but that's actually what you should do, right? Okay, and I will show you some examples. And in the middle, it's an interplay between high entropy and low formation enthalpy, and then you need to pretty much study both of them, and the entropy and enthalpy, and see which wins. Okay, and today I will show you some big data analysis that allow us to discover entropy stabilized oxide, and here high entropy carbides. So there are two different types of materials, and in which there is data available. Okay, so now the real numbers. The numbers are this was like a cartoon. The real numbers is this. Okay, so if you mix two species, the expectations of formation enthalpy is 185 milli-electron volt. If you mix 3 species, is 7 milli-electron volt. If you mix 4 species, is less than 1 milli-electron volt per atom. And that's why, at least these are for metals, an example. So that's why if you look for Euslers or for quaternary Euslers in the ICSD database, most of them are actually very disordered. Okay, because at the 3 and 4 species, pretty much in metals, everything is really, really disordered, right? For ceramics, we need a few species more, but the idea is the same. So this is a disorder driven transition by, a species driven transition to order disorder. Okay, so this is the flattening of the configurations. So you see that even if the enthalpy, even if the number of configuration increases exponentially because you have more species, so you can arrange them in more ways, their delta shrinks dramatically. So when you do the convolution between the number of alloy systems, right, which grows exponentially, you see this is a log plot with the histogram of the enthalpy gain, you see why you have a flattening of your stability toward disorder, and that's why it's pretty much hopeless to look for order system at many species. Okay, this was in disagreement to what people believed 10-15 years ago, where they said that the species of the space of configuration order was increasing. Actually is not with number of species. Actually is dramatically decreases, and this actually was very good for us. Okay, so this is another example. If you take a 4 species systems, and we have a 113,000 phase diagrams, and you can reproduce this with Nomad, you would even get even more than 100,000. You will find that only 50 of them actually have a stable configurations that are ordered, right? You see how the red versus the blue becomes the red shrinks dramatically, and this is a log plot, right? So that's why you just say, well, who cares about this 50, and you just embrace disorder and find what you can do with disorder. So the first things we did was to test, well, is this bogus? Is this real? Because this is really crazy. So we went on with some our collaborators, and we tried this idea of n to n+1 phase transition, order to disorder with oxide. Okay, and if we find something, right? And this was a completely experimental work that we did in 2015, 2016. Okay, so what did we do? Okay, first of all, as I told you before, we neglect enthalpy. Okay, that's it, no calculations. And then we also neglect the entropy, so we take the ideal. So the task now was, does this transition exist or does it not exist? So we take a bunch. At the time we took only 5, but now we have 8. Some of these are more expensive, like scandium oxide. Anyway, so we took a bunch of metal oxides, right? Those have all powders. And then we take n of them, we mix them, we cook them, and then we see what happens at high temperature if there is this order-disorder transitions with n. And then we do, if nothing happens, we do with n plus 1, okay? And we repeat the process. That's actually is very simple. Does it happen with n or not? Does it happen with n plus 1 or not? Yes, it does. And we found that the threshold was to go from 4 to 5. So every 4 of these 8 metal oxides do remain phase separated at around 1000 Celsius, okay? But if you take 5 of them, any 5 of them, you have the miracle. This creates a solid solution. Examples, all right, this is the first example we did. We took equicomposition to maximize entropy. So so you see that at low temperature, each one you have the fingerprints. This is 2 theta, right? You have the fingerprints of the powder of the precursors. All this that we can do now with AFlow or Nomad, we can find all the peaks in the right place. You increase the temperature, and then you have the miracle at around 900, 1000 Celsius, okay? And everything becomes rock salt. You see the typical lines of the rock salts, okay? Entropy-driven transition. It's like melting, okay? But the melting ice to liquid water is reversible. You go down, you have ice. You go up, you have water. So if we go down in temperature, again, the miracle, right? You have the decomposition in the powders, and you can go up, you can go down, you can go up as many times as you want. Okay, which is very important, because every time you have a transition which is entropy driven, entropy times the change of entropy times the transition temperature is a latent heat, which we can use in a heat pump. I will show you later an example, right? Okay, so this is reversible. Then we change, we check if with differential scanning calorimetry, but that's not important. So so more proof that was an entropy transition, so it was reversible and endothermic, etc. And then another test to check if people talk about entropy stabilize, entropy transition, but is really entropy? You need to check where is the transition temperature with respect to entropy. So the best way to do is actually very simple. If you are equicompositions, maximum entropy is at equicomposition. So where S is max, T is mean, because you are fighting against a constant enthalpy. We neglected it, therefore it's constant. So if you go off max S, then T will change. So you see that we did some sort of cross-validation by changing the composition of the constituents, and you have T mean where S is max. Okay, so when you go off stoichiometry, right, well, off equicomposition, the transition temperature increases. So you see that is an example of experimental big data, because every one of those V shape took many experiments. Then eventually everything went online, and then recalculated, and all the data is available. So this is another example that is really entropy driven. And on top you have rock salt, and on bottom you have the composition of original phases. So if there are thermodynamists like me, so those are 2-dimensional slices of a 5-dimensional eutectoid. So a solid solution above and the composition on the bottom. So as I told you before, applications, all this entropy stabilized oxide actually opened a new family of studies and the materials, and actually it was discovered that actually were very good, right, for doing actually heat pumps. As I told you before, when you go up and down in the transition, you are heating and cooling, so you are actually pumping in and out heat, but the chemical properties of the low temperature phase are different than the high temperature phase. So pretty much you are able to split, chemically split water, right? Because a low temperature water splits, but you have a release of hydrogen remains inside, but at high temperature you have oxygen goes out because the rock salt cannot keep oxygen inside, and then pretty much you transfer the heat of the decomposition of water through this heat pump going up and down in temperature through these materials, right? So the idea is that if you're interested in catalysis, if you are able to reduce this temperature by better oxides to temperature like generation 4 nuclear generators, right? We would be able to generate a lot of free hydrogen and oxygens, right? Anyway, so this was like a spin-off work by other people. Anyway, so the idea, all these things was, all this data that at the beginning were experimental, we recalculated it to find better materials, and it's all available online, so you can get it through AFLO or Nomad, okay? So then the other side, right, the middle part, right, the high entropy part, right? So we are reducing a little bit the number of species. And this led to the discovery of high entropy carbides and some theory that we had to do it to get them, right? So it's and then the evolution of this was studying vibration, etc. Right? So first of all, we need to define disorder. So if we want to go beyond x log x in entropy, we need to have a defined disorder and then find some sort of spectral analysis of the disorder. As you know that from Boltzmann, the entropy is the degeneration of the state. So we need to figure out a way to recycle the Boltzmann descriptor into some more modern big data form. So first we need to define what is disorder. And for us, disorder actually is quite simple, is the decomposition of a local order, which is kind of obvious, right? So big disorder, think about that you're painting your garage, right? Putting tiles on your garage, and you kind of put in tiles randomly, right? Black and white, green and red, etc., etc. So every one of these tiles is order, and you have as many as possible and as large as possible. Okay, so if you have a large and many, you really reach disorder, because disorder is macroscopic, but we cannot calculate it, right? So you calculate only as many or only as large. So, but now you have a choice. Okay, you have the choice to make a few big cells, and this is the strategy of SQS, which I will talk in the next slides, or many small cells, which is the strategy of the partial occupation ensemble that we developed in 2015, 2016. Okay, so if you have many and large, SQS and POC will give the same answer. But if you are limited in the number of computers, which means electricity, which means resources, then you can choose to make many or large, because the large is going to give you some properties, the many is going to give you other properties. For instance, I'll tell you why we chose the many, because it gives the phase transitions, okay? And then we show you later why. Okay, so if we do the many order structure, you need to generate them, right? So what do we take? We take the cell, right? This is the disorder cell, the conventional cell. This is some sort of in VASP language. This also works for quantum espresso or Rabinit anyway, right? So you write your unit cell, and instead of occupation with a number of atoms, you write like 3.5 or 7.2, right? You add the occupation that is partial, right? Then you crunch it through AFLO, right? And the AFLO is going to generate, you write a cutoff. It generates a lot of supercells that are which are compatible with the composition that you have chosen, right? It generates all the supercells with the Hermite normal form enumeration. Will generate all the little examples, snapshots. Will get from the factor group, the degeneration, will calculate how many you have, because you don't need to calculate them all, right? You have repetitions, okay? For instance, you might have 100 of those, but only 10 are unique. So you really need to be careful picking the unique ones. And AFLO does everything: enumeration, normal form, and the calculations, right? And then once you have all this snapshot, you actually calculate them, and they all go with some protocol They all go on our websites where you can download them, and you could even calculate cluster expansions as people have been doing, or potentials if you are interested in generating potentials for carbides in this case, right? But once you have all of them, okay, you calculate the ground state, which is going to be done with the convex hull, and all this H, which are the thermodynamic excited states. Okay, so now you have this P, which is kind of a probability, and it's multidimensional probability, right? So because for every I, you have G, and then you have P. So you have a multidimensional probability, which is like a probability in the space of probabilities, right? A vector, and then you normalize, so everything becomes one, right? But that's okay. Don't worry about the denominator. Okay, what do we do with this? All right. Okay. First, why as we prefer POC instead of SQS? Look actually carefully SQS, how SQS is generated. SQS, a special quasi-random structure that was made in the 90s by Zunger et al., okay, is they scan all the possible configurations that are generated, okay, the configurations, and then they calculate the interactions through the cluster expansions configurations, right? Okay, so you have the 2-body, the 3-body, etc., etc. And then since within you can calculate analytically this configurations for correlations, they're called correlations. For the ideal disorder, if you have a 2-body and you are half and half, you have 50-50, then you're gonna have 1/2 times 1/2, so 1/4. If you have a ternary, okay, you're gonna have 1/3 times 1/3 times 1/3, right? So you can always algebraically calculate this coefficients for the ideal disorder. And then of all the possible SQS that are generated combinatorially, okay, later, for instance, Axel van der Walle tried to generate them stochastically because the space becomes gigantic, okay. Anyway, all the possible configuration, you pick the one that resemble the most the ideal disorder configurations through these correlations. Say, okay, so if these SQS, okay, so the special ones are the ones that are as close as possible to the ideal disorder, and the ideal disorder is the one that you have an infinite temperature. So SQS does not represent the low temperature disorder, near phase transition, but can only represent infinite temperature disorder, far, far away from the order disorder, and therefore represents perfect disorder, where you have already you reach thermodynamic equilibrium, therefore the Dulong-Petit formula, where all the degrees of freedom have been excited, there are no precursors, there is no latent heat, there is no phase transition. SQS is the perfect method to study isomorphous disorder, silicon germanium, where everything is really pretty much the same. But if you reduce the temperature, cannot give you the precursors of that you start seeing when you hit the miscibility gap. And therefore, these things does not have a spectrum, because all the enthalpies should be pretty much the same enthalpies of the disorder, and therefore has no entropy. The only entropy you can get from SQS is from the Dulong-Petit formula. So that's why we chose POC, because even if the cells are small and we might lose some long-range precursors type, we get the phase transitions, because we get all the spectrums, because all these H are different. So for SQS, all these H are the same. For us, all these H are different. So we get the P. Okay, that's why we like POC. So now, oh, by the way, there are also some advantages with respect to amount of electricity. So since the number of time, which is equal electricity, which means euro or dollar, it goes like with the number cube of the electrons, free electrons per unit cell. Then you see that if you look for order disorder in this direction, is cheaper than if you look in this direction and you need to reach this side. Okay, but that's okay. So this is from a monetary point of view. Okay, so now that we have all these cells, right, all this H, all this P, what is the entropy? Well, we need to make some guesses, because we really do not have all the calculations. You have only a finite number of them. So this dots are the one that you get from this from these excited states, right? And this blue is what you get from the convex Hall analysis. Okay, all this data available online. There are thousands and thousands of them. Okay, so now what do you do with these things? Remember that Boltzmann said that the entropy is the degeneration of the states. Okay, but that's not really. It's not really. This is only if the states have the same energy. But if the states have a more or less a similar energy, then that is not a good definition, and you need to go to the Gibbs definition of entropy, which says that SEDE is K, of course, log of omega E DE. So you have this DE, which is the bin, which is the energy between energy and energy plus delta energy. So once you have the number of states between energy and energy plus delta energy, which is this omega, you make all this big log, and then you get S times dE. So you remove dE from both sides, and then you get this S. Okay, so the idea here holds the same, but since we don't have we have not spanned infinite number of the configuration, but only finite, we pretty much take the number of configurations that you have between E plus delta E, and this is what we call this thermodynamic density of states. If the thermodynamic density of states is as a peak is very thin, then you have a high entropy. If it is very broad, then you have low entropy. That's simpler than that. Okay. Since we don't have we don't have infinite red ones, so we don't dare call it entropy. So we call it entropy forming ability. So we measure this degeneration with the variance of the spectrum, okay, and we call it entropy forming ability, okay. So if we had infinite computers, this would really be entropy with all the properties of extensivity, etc., etc. But since we don't dare call it entropy, so we just call it entropy forming ability, and should behave like entropy. All right. Remember, there is a lot of technicalities. You need to calculate all these things. You need to calculate all the G's. So it's harder to do than to say. But the idea is actually simple, right? And you can get all these tools online. And we also have an AFLOW school that teaches how to use it. Okay. Eventually, you're gonna get this entropy forming ability for every compound. Okay. So now let's discover new compound with big data. So every one of these refractory carbides, okay, so you have eight refractory metals plus carbon, is split in a group of 5 metals plus carbon, right? For each of that, we actually calculated roughly, okay, there are 50 of them, we calculated roughly 100 snapshots, all right? Then from the snapshot, you get the entropy forming ability, and we order them through the entropy forming ability. Then we also plot the formation enthalpy, which is really this distance, the distance between this and the center of the peak. Okay, so consider this as the enthalpy loss and this as the entropy gain. So we go to the experimentalist. Remember, at the end, what counts is the experiments, because if we do not have the material, then everything we do is really hot air, right? Okay, and we go to the experimentalists. We don't tell them which one is good and which one is bad. They do the experiments, and they discover that the one with high entropy forming ability actually do form with a solid solution, and the one with low entropy forming ability do not. Okay, so this is already a success, but the biggest success of big data, and it's good for all our community, it comes from the analysis of the first two. Look carefully the first two. Let's start from the second one. This is a blah, blah, blah plus carbon. Okay, all these metals, carbides, okay, their precursors are cubic. Okay, so hafnium carbide, niobium carbide, they're all cubic. And guess what? You are mixing cubic tiles. What do you expect when you're going to have a cubic outcome? In fact, this was predicted a few months before us because this comes from phenomenological analysis, right? You say, well, I mix cubes. What I'm going to get? I'm going to get cubes, right? With some strain and stress inside. Fine. But the success of big data is actually the first, because both molybdenum carbide and tungsten carbide, they are not cubic. One is a rhombohedral and the other is orthorhombic. So practically you're mixing 3 cubes plus a bunch of hexagons, plus a bunch of orthorhombic things that are like elongated parallelepipedi, you don't expect to get a rock salt, but still you get it. And this was completely unexpected. And this is really a success of this big data analysis that led to other research. And even if the entropy, even if the loss in enthalpy is high, then the entropy forming ability was so strong that we could form these materials, right? And actually, this is an example of these materials and how we are making them. Let me go quick so we do not go out of time. And this material really exists, okay? And there's some weird mechanical properties that we are kind of studying. Okay. The last analysis of big data actually came if we really wanted to get the miscibility gap completely, really get it from an analysis of big data and thermodynamics. And this is the method LTVC from Lederer, Toher, Vecchio, and myself that we did a few years ago. Okay, so first of all, let's understand where miscibility gaps come from. So in an isomorphous system, A and B loads each other. So you have this alpha, right? But if A starts hating B, is like Duke versus UNC, right? A likes more A, B likes more B. So at low temperature, there is this kind of segregation. So you need to increase the temperature to start mixing them. Okay, you see where you have solid solution. So if the hate between A and B increases, then these miscibility gaps go up until they touch the congruent melting here, and it forms the eutectic or eutectoid phase diagrams. Okay, so this was already known for a couple hundred years. So the clustering tendency of the solid given by the hate between A and B creates a high segregation, the hate, and therefore melting depression of in the liquid. Okay, so what about if we are looking for super high temperature materials? And that's why we were sponsored. If you are God and you are able, and you already have a solid solution and you have a little bit of miscibility gap, and you're able to put your finger on the miscibility gap and bring it down, wow, I bring this down, so I'm going to bring up the congruent melting. And that's why we were studying this miscibility gap, because instead of calculating the melting point of these super high melting materials, or even making the experiments, how can you make the experiments of a 4,000 Kelvin object, melting object, right? It was much cheaper to guess the miscibility gap, okay, and find a relationship between this point and this point. You just go in literature or with calculations, you find a relationship between this arrow and this point, and then you are done. Okay, that's what we were doing a couple of years ago, right? So instead of getting a very high melting point, you get a very low miscibility gap in system forming solid solutions. Okay, that was the trick. This came from analysis of literature, the books that Matthias mentioned before, where they were all already digested in CALFAD and in the ASM phase diagrams books. Okay, so then plus we did some extra CALFAD, and you see that if you increase the number of species, actually you increase the melting point. So you want to increase entropy and make the materials more refractory, right? So more species and more refractory, but at the same time more mixing. In fact, if you look at the materials with the highest known melting point, which is this one, right, tantrum hafnium carbide, you see the melting point is half higher than its precursors, tantalum carbide and hafnium carbide. So this is you just get roughly 60, 100K, depends on the experiments. And guys, well, audience, making the experiments to really measure these things is highly non-trivial, because you cannot put this on a crucible. It melts. So you need to have this material, you need to suspend in argon, like argon, and then shoot a laser and then look for a reflection. You see if you have a melting or not. This is a highly non-trivial. Okay, so you can do better machine learning than us. This is really an interpolation. If you use CISO, okay, you can put more features, okay, and you're gonna get a better estimation of the machine of the melting point. And if you want to understand more what people are doing for machine learning for alloys, you can read this recent review that came out a couple of months ago, right? It pretty much contains all these things. Okay, so now let's go back to the big data. What do we do with this P? All right, okay. And why we chose P. First of all, okay, we want to get the disorder transitions, okay, and you have these grand potentials, right, with our probabilities. You don't know what they are, and we will find what they are later. This is you guess some entropy, which has the the macroscopic concentration plus a change, and a change that you don't really know what it is, but we will discover what it is. Okay, and then you make this the calculations, right, because you need to get the generation. Every tile has the microscopic compositions, and the microscopic composition sum needs to be the macroscopic. So this is pretty much the generation of every tiles, right? Okay, so you can read this article, it's kind of obvious. Once you do this and you minimize this grand potential, and you have all this J calculation, there are millions of them, right? And you can get them online, right? You do with the Lagrange multipliers, and then you find that you pretty much have what is called the A-flow population vector. This is exactly the P of before. Okay, remember the P of before, sorry, it has this part, well, with the normalization, but before it was a probability based on enthalpy. Now we have a probability based on Gibbs free energy, sorry, because we are removing the chemical potential. So it's exactly the same things. So you see how the power of POC and these energies. By the way, if you can put our energies, POC energies, but if you want to clusterize them, as we did in this article, you have more of them. And if you want to add the machine learning, you just, the more the better, right? You're going to have a gigantic population vector, okay? And you just do all the normalization, and you see how this vector changes with respect to temperature. And this will give you your order disorder. So machine learning, cluster expansion, A-flow, NOMA, everything goes here on this epsilon. You do all this operation, and then you're going to have this gigantic vector, and you see how it moves in the space of probabilities, and find your phase transitions. Here it is. At infinite temperature, okay, well, let's go to the simple one, zero temperature. Zero temperature, you have only 1, 2, or 3 phases appearing. So the vector is well defined, right? At infinite temperature, and you look at my arm here, you have everything is equiprobable, right? Okay, so the vector is going to be in different directions. So if you reduce the temperature here, the vector changes. You see, reduce the temperature, the vector changes slowly, but actually moves slowly, bam, until it has a big jump. Okay, and you can calculate how much this vector moves with respect to a reference. We took the infinite temperature because it was much easier, right? So we don't need to do the phase diagrams, right? And then you see, and if you plot the gradient of the angle with respect to the temperature change, right? You see that actually these things moves. It really moves very, very, very slowly. Bam, it jumps. Okay, so when it jumps, you have the phase transition. You define the phase transition in the position where you have this big data calculated population vector jump, and that's it. You really have the phase transitions. So the phase transition is going to go, you're going to go down, you get this point, okay? At this point, you're going to get the change of entropy, the entropy that is above, the entropy that is below, okay? This is going to be the second part of your S, which is called the Kullback-Leibler divergence. And then you say that the amount of relative entropy that you have lost, not the amount of absolute entropy, but the amount of relative entropy. You say, I lost 30%, I lost 50%, whatever it is, okay? It's the locus of the relative entropy loss is equal, right? Is going to be your miscibility gap. Guess what? It works amazing. This is for tantalum zirconium, for niobium zirconium, for copper gold. Look, our calculations, which takes weeks, okay, are those, and this miscibility gap can take years. Think about the miscibility gap of copper gold. After hundreds of years has not really been found well, because at low temperature these quantities are very hard to be found. Anyway, once you have the miscibility gap and you have the machinery to get to the melting point, then you are done. You really have the low part of the phase diagrams and the high part of the phase diagrams, and you're already exploring phase diagrams with big data. It's very simple. This is a statistical analysis, how well it works. Okay, this is for all the phase diagrams, but excuse me, if you only look for the low part of the phase diagrams where we want to reduce the miscibility gap, actually works very well, right? Then the question is, and then leave the interested people to the literature. Now the question is, people keep asking, what about vibration? What about vibration? And high vibration important or not? Do we have a entropy stabilized, vibration entropy stabilized? This is something that we were talking with Matthias a few years ago, and sometimes it does, sometimes it doesn't. And this is an article that is in press in Nature Communication, should come out in a couple of days, and tells us for the case of carbides, when vibration are important. So what did we do? For all the carbides that we had, we have where we did the EFA, so we had 100 carbides. For all of those, we calculated all the spectra, right? The phonon spectra. And then we see which one are important and the one are not important. So think about the amount of calculations. You have 50 carbides, you have 100 EFA for each, and then you have roughly like 100 phonos calculations each, right? So it's a gazillions of data that it all goes online that we can reuse it to calculate the potentials, as people in this in the audience are much better than us doing. And we can calculate the change in the phase diagrams due to vibrations. So this is the article. Yes, I'm done, right?
Come to an end.
Yes.
Please.
Okay, I'm dying with the next slides, right? So this is the article, and this is the solutions, right? So we did the POC with the harmonic. We are able to calculate all the density of states, and we are able to show that the formation enthalpy, okay, so can be neglected if the precursor have the same symmetry. If you're mixing cubes with cubes and you get cubes, neglect the vibrations. If you're mixing cubes with hexagons and you get cubes, then you need to take care of vibration. And this is the message of this paper. Okay, then we did also an harmonic, but let me end. Okay, so now I end. So we have a couple of minutes for questions. We are equipped with our websites for our repositories, and we are just generating descriptors to find these disorder materials. We are interested in ceramics, so oxides, carbon nitrates, and carbides because of our funding. You can look at ceramics and what we are doing and the methods in these two reviews. And a very short summary will be in MRS bulletin in February 2022. And I want to thank everybody, and I'm here for questions. Thank you very much.
Okay, thank you, Stefano, for quite a lot of material. Questions from the audience? Write it to the chat, or in fact, just simply raise your hand or start talking if you want. Any questions from your side?
Yes, Matthias, I have a question.
Yes, Tom.
Thanks. This was a lot of information, and I enjoyed it very, very much. I do have a content question. I did not quite understand if you make ceramics, you can have site disorder, and I think that you would only using site disorder as your description. But in addition, this order disorder transition can also be driven by bond disorder. Is that taken into account, or is that not taken into account in your description?
At the beginning, we don't take it into account, and then once we find the perfect solubility, we start looking if we have a distortion on the lattice that indicates what you call the bond disorder. We have not found them for carbides, but we did find them in oxides around the copper. Yes, that's correct. So this is a order to check, and then it's not in the theory we showed today, but we test it. That's correct. Yes.
Because I understand that many ceramics are being driven by bond disorder, especially to optimize the local structure and not so much to keep on the global structure, but to optimize also the local enthalpy. So it's local enthalpy driven. And then that is a driving mechanism for the disorder transition.
Okay. So listen, at the end, even if we neglect the enthalpy, at the end, the enthalpy should be considered, because the entropy is fighting against the enthalpy, so it gives the temperature. But yes, we do check these things, but not at the beginning of our materials discovery, but on a secondary analysis. At the beginning, we just do all configurational. We increase the number of species, and then we increase the temperature, and then we find that this material works, this material does not work. And then on the materials that do work, we slowly reduce the temperature, and we do the analysis that you're mentioning to see if it's really entropy driven or if there is enthalpy, local entropy contribution. That's correct. We do this.
Okay, thank you.
But we discover only for oxides. We have not discovered for carbides. That's the answer.
Okay. Thank you. So Moritz to Baden.
Yeah, thank you very much for the inspiring talk as ever. I was intrigued to see the copper gold, that this one behaves similar as the others, because the copper gold system is actually not a disorder or order disorder transition, or not a demixing, but it's an order disorder transition, right? You have the 3 different ordered states of the copper gold system. So I was impressed to see that. I don't know whether you have a comment on that. Do you expect this to work always like this?
Okay, so thank you for the killing questions. Yes, you're right. These are not one miscibility gap, but there are 3 miscibility gaps here that are convoluted. Okay, we did not have. Okay, so look carefully how we do this. Right, we just pick one positions, and then we calculate the entropy, and then we claim one miscibility gap. If we know that there are 3 miscibility gaps, we should do a lot of lines going up and down, and we would pick 3. But for the purpose of this article, we just extrapolated and we picked one. So which miscibility gap here we get pretty much the convolution of the 3 that we have. But yes, there are 3 miscibility gaps in copper gold.
It's not a miscibility gap. It's an ordering transition. Miscibility gap is, I mean, below the black line, you have 3 different one-phase regions.
Well, no, it's not really. You don't have a one-phase region, because if you have one-phase region, this should close in a copper 3 gold or a copper gold 3, right? It does not close like this. So it does. Well, let me tell you, that's still debatable. But okay. So what happens here? We don't know. We are interested in what happens on these black lines, and our red and green line represents some sort of convolution of the three order disorders that appears. Then what really happens below has been debated for many years.
Okay, actually, another thing that you might want to look at after you have already can make a check mark on the vibrational contribution, defects, point defects, so vacancies of carbon, vacancies of metals, or maybe even other more complex defects in the carbides. You always have an off stoichiometry, right? I mean, that also makes the experiment difficult. Yeah, did you ever look at this?
Absolutely. Okay. So the entropy gain given. Okay, of course, a vacancy is an extra species. So we do this calculation with an extra species, which is called X, lack of something, right? And then I can tell you that for contribution of the configuration contribution of stabilizing contribution of vacancies of metals is negligible. There are, but we just don't bother, right? There are. For what concerns the carbon contribution, it does. Okay, for in case of carbides, and they're very important high temperature. For instance, if we go here, like here, if instead of having 5, you have 5 nano X, you have what is called reciprocal system. So you have entropy in the metal sublattice and entropy in the carbon sublattice, and actually you can increase the melting point a little bit, okay? And you can also increase ductility, because this material tends to be very brittle. So yes, for the carbon vacancies is important at a very, very high temperature near the melting. For metals, in the case of carbides, don't bother. In the case of carbides, for oxides can change.
Okay, thank you.
You're welcome.